Okay, so we are in Causal. If I can get my scroller up here. We're in Causal Inference and Statistics, that book right there, and we're all the way down on question 2.51. It's a multi-parter, so we'll look at them one at a time, but they all center around this DAG right here, and it's reproduced a little, below, so we won't have to continually scroll up. Okay, so here's 2.51a. All right, so looking at this figure 2.9, which of the arrows in figure 2.9 can be reversed without being detected by a statistical test? Okay, it tells us to use the criterion for equivalence class that's given in the chapter just a little bit before this question shows up. Okay, so what is, let's talk about what an equivalence class is, okay? So it's a set of DAGs that have the same nodes, okay, and edges, i.e. arrows, regardless of the direction, right? So an edge from X to W is the same edge as an arrow from W to X. That's the same edge, okay? And the equivalence class also has the same V structures, otherwise here known as colliders, right? So a collider is where two different variables impinge on another variable, right? So Z1 and Z2 impinge on Z3, so that's a collider, okay? The V structures whose parents are not adjacent, but we can, I think, kind of ignore that. I think we get the gist with just the V structures. So in other words, the equivalence class of this DAG is going to be any DAG that we can make by simply reversing the arrow, and that does not cause or eliminate existing V structures, existing colliders, okay? Now, when you go through this, though, let's just do a couple here, okay? So let's try to reverse the arrow from X to Z1, right? So now if the arrow goes from X to Z1, we have eliminated a V structure here, a collider at X, okay? So we can't reverse that one. Okay, what about the one from Z1 to Z3? Well, if we reverse that one, again, we're losing a collider here. Okay, well, what about from W to Y? Well, we're losing a couple of colliders, WYZ3 and WYZ2, and we're also creating a collider at W, right, XWY. And so if you go through every arrow here, what you'll actually discover is that there are no arrows that we can reverse without either losing or creating different V structures. So zooming out a little bit, that means that the equivalence class of this DAG is just this DAG. This is the only DAG within this equivalence class. Okay? And so that means then that in principle, that the direction of every arrow here could be detected with some kind of statistical test. Okay? All right, so let's go on to B here. So list all graphs that are observationally equivalent to the one in to figure 2.9, the one we've been dealing with here. Okay, but this is really almost just a restatement of the previous answer. Okay, we found that there are no other DAGs except for the one pictured that are in the equivalence class. Okay, and so there are no observationally equivalent DAGs for the one that we have here. And then again, here in C, this is really just a restatement of at least part of the answer to part A. List all of the arrows in figure 2.9 whose directionality can be determined from non-experimental data. Okay. Again, because the equivalence class is not ambiguous, in other words, that's a weird way to say that, because there's only one DAG that could produce, how do I want to say this? If we had data that came from this DAG, only one DAG could have produced that data. That's a weird way of saying it, anyway, we can determine the directionality of all arrows from non-experimental data. Okay, part D here. I find the wording here a little bit awkward, so we'll try to work through it. But we want to write down an equation, a regression equation for y, for this guy right here, such that if a certain coefficient in that equation is non-zero, the model in figure 2.9 is wrong, okay? So in other words, maybe we have some data and we're hypothesizing that this is the DAG here, and we want to find some ways to test if this DAG is, supported or not. Okay, and one of the ways that we could do that is to look for conditional independencies, and then look to see if that conditional independency holds up under regression. Okay, so for example, if I'm looking at y here, and according to the DAG, well, y should be independent of x, assuming that I condition on w and I think z3 here. Okay, so I can put that into my regression equation. I can have beta x times x, beta w times w, and so on for these other variables here. Okay, and if the DAG is correct, then this beta x term should be 0, right? Because x is independent of y given w and z3. All right. Now, so if that is non-zero, right? If that certain coefficient is non-zero, then the model has to be wrong. It means that there's, some other set of paths. Hold on. Okay, and we're back here. So, anyway, where we left off, which is instantaneous for you, but I'm catching myself back up. But we find that x should be conditionally independent of y given wz3. So in this regression right here, beta x should be 0 if the DAG is true. Similarly, z1 should be independent of y given w for sure, given z3 to block off this path, but once we condition on z3, notice that we open up the collider that opens up the path from z1, z3, z2, y. So we'd also need to condition on z2. Okay, that's fine. So we get this type of regression, and if the DAG is correct, then this guy right here, beta z1, should be 0 if the DAG is correct. Okay, and we could do that for any variable here that has a conditional independency. Okay. So in part E, we are asked to do exactly that. Okay, we're meant to repeat part D, but for variable z3 here. All right, so we need to find a conditional independency, and I think that the only one is that z3 should be independent of w given x. Okay, and so the regression should look like this, and again the beta w should be 0 if the DAG is correct. Okay. So now, for part E, we need to, again, do part E, which was a repeat of part D, but for variable z3. Okay, but now we are assuming that we cannot measure x. Okay, so let's go back up here. So we need to construct a regression where we are trying to, see if beta w can be, well, maybe not beta w. Here, w is I think the only thing that is conditionally independent of z3, and it is only conditionally independent given x here. And so if we can't measure x, the question is, can we still find a regression that could test that? And here the answer is no, because the only link between w and z3 is x. So if we can't measure x, we actually can't measure, or we can't, we can't run a test on that particular conditional independency. Where are we at here? That was part F. Okay, part G. Okay, part G is another mouthful here. So how many regression equations of the type described in D through E? And again, what were we doing in parts D through E? We were looking for coefficients in a constructed regression equation that should be 0 if the DAG is correct, and if they are not 0, then the DAG is incorrect. Okay. And in those cases, we were focused on variables y and z3. Okay. But how many regression equations of those types are needed to ensure that the model is fully tested? Okay, so by the model we mean the entire DAG, not just w, or I'm sorry, not just y and not just z3, but every variable in there. Okay. Namely, that if it passes all of these tests, it cannot be refuted by, there should be a by there, I think, by additional tests of these kind. Okay. So hint, ensure that you test every vanishing partial regression coefficient that is implied by the product decomposition. Vanishing here, I always struggle with that term, but it just simply means that the regression coefficient should be 0. I don't know why vanishing is used, but it seems confusing. It seems like a verb rather than a noun, I guess, or an adjective. Okay, now, so it suggests that we use the product decomposition, and admittedly, that's not the way that I would start this, but let's start that way and just kind of build out from there. Okay, so let's first decompose this DAG. Okay, so we have the joint distribution of all variables being decomposed as such. Okay, and you'll notice that the way I've decomposed this, Z1 has no parents, and so the probability of Z1 is non-conditional. Same with Z2, it's non-conditional. Okay. Z3 has 2 parents, Z1 and Z2, according to the DAG, and so it has that conditional structure. X has 2 parents, Z1 and Z3, and so it has that structure, right? W has 1 parent, X, and Y has, 3 parents here, W, Z2, Z3. Okay, so we've decomposed that. And so now what we are going to try to do is to see if we make a, how do I want to say that? We're going to find regressions, right, for each of these variables here, where we condition on the parents for 1, and then look to see if that renders the outcome variable independent of all of the non-descendants, okay, as according to the DAG. Okay, so let's start with Z1, and actually we're going to do Z1 and Z2 together, right? Because I guess it's not really conditional independence here, but Z1 and Z2 should be independent, okay? And so we can actually we can regress one on top of the other here. That would be one way to test this, right? Well, how do I want to say this? Z1 and Z2 should be independent, and Z1 is not a descendant of Z2, nor is Z2 a descendant of Z1, right? Everything else is really descendants of these guys. And so we want to see then if we regress Z1 on Z2, if we find dependence between the two. If there is, then our DAG is incorrect. Okay, so we could just run one regression. We can pick either Z1 regressed on Z2 or Z2 regressed on Z1. Okay, so now we'll go to Z3. Okay, so we'd want to regress on the parents, right? And then see if regressing on the parents renders it independent of all of its non-descendants. But aside from Z3's parents, Z1 and Z2, everything else is a descendant of Z3. Okay, so there's not really a test that we can perform here for Z3, or at least a test of this type. Okay, so now we are on to X. Okay, so the only variable that is neither a parent nor a descendant of X is up here in Z2. Okay, so if we condition X on its parents, Z1 and Z3, and then also include a term for Z2, then the beta term, the coefficient for Z2, should be 0 if the DAG is correct. Okay. So what are we on now? Okay, so now we're on W. Okay, so W's only parent here is X. Okay, and its only descendant is Y, so we're not going to include Y in the regression. So we're going to include everything except for Y in the regression of W. And once we regress on X, then the beta coefficients for the other variables, Z1, Z2, Z3, should be 0 if the DAG is correct. Okay, finally, we are at Y. Okay, Y is a descendant of everything, so it has no descendants. Okay, and its parents are W, Z3, Z2. And so that means that if we regress Y onto W, Z2, Z3, as well as its not parents, not descendants, Z1 and X, okay, then Z1 and X should be 0. Okay, in fact, we already saw this one above. Okay, so Anyway, that is the answer to G, and we will call that good.